Hello and welcome to this presentation on DirectX11 Math. I'm making a separate presentation on this because in DirectX11 they've added some math functions that are a little bit different, that take advantage of special hardware that's available on a lot of computers these days. In particular, we want to start out by looking at the difference between what they call a XM float type and an XM vector. And the first case, the XM float 3, is a three-dimensional vector defined as a structure with x, y, and z coordinates. The XM vector is a different data type that's actually aligned with a special floating point register on the CPU. And so I believe it's a 128-bit register that you can divide into 4 32-bit floating point values. And these registers that are available on a lot of CPUs these days have the capability of doing what's referred to as SIMD instructions, so single instruction, multiple data. That's what SIMD stands for. And basically what this means is that the 4 values X, Y, Z, W in this floating point register, for example, you could take 2 of those and add those together, and it would add the 4 values in one register and the 4 values in the other register in a single instruction. And the performance can be significantly improved taking advantage of these SIMD instructions that are available on a lot of processors. The downside for us as programmers is that we end up having 2 data types, and sometimes it's not clear which is best, which one we should use. My recommendation is that for vectors that are going to be placed into vertex buffers and transferred over to the GPU, that we use the float 3, float 2, float 4 types for 3D, 4-dimensional, and 2-dimensional vectors like texture. And if you're going to be doing significant processing on the CPU, for example, a camera position may change regularly, a camera look direction may change regularly. The processes that you want to do on the CPU, store them as XM vectors. And I haven't measured it, but my assumption is the performance of doing operations on XM vectors would be better than doing operations on float 3 types. In particular, DirectX doesn't really have the common vector operations for something like an XM float 3. You've got to convert it and then do the operation. But you could write it your own. You could write it yourself. My assumption is that the performance would be better with the XM vector taking advantage of the special SIMD instructions. So let's take a look at the documentation. If you go to Microsoft MSDN and look at their DirectX Math programming reference, you'll see there's a variety of different sections. The one that I commonly use are the library functions, and you can look at the structures and classes associated with them and the types, but most often I use the library functions. And in there you've got several sections. So there's a section on matrix functions, there's a section on vector functions, and there's a section on accessor functions, and those are the ones that I use quite a bit, and maybe the store functions as well. The matrix functions, as we've seen in some earlier programming, one of the common ones that we'll use is this matrix look at left hand to give us a view matrix. We can use the XM matrix multiply, but I believe the asterisk operator is overloaded to do this as well, so it reads a little better by just using the multiplication symbol. The perspective field of view left hand will give us a projection matrix. That's one that's commonly used. And then we can get a rotation matrix to get us a rotation about a particular axis, rotation about XYZ, scaling matrix, translation matrix are also really popular. So the basic matrix operations that I commonly use are scaling, rotation, translation, an identity matrix, a view matrix, and a projection matrix. So there's only about a handful of those that probably you end up using 90% of the time. On the 3D functions, they've got vector geometric and vector transformation functions. Here, if you look at the geometric functions, some of the common ones that we see are dot product, cross product, vector length or magnitude, normalize. These are ones that are commonly used. The transformation functions will allow you to transform a vector by a matrix, or perhaps rotate a vector using a quaternion. If you already have the rotation in a transformation matrix, then this one will work well. That's probably one of the more common functions to use. The accessor functions, this is where we go back to this point about how the XM float types are easily accessed with .x, .y, and so on. The XM vector type is not, because it's mapped to a floating point register. It has some weird member variables. So in order to access, say, the XYZW component of an XM vector, you would use these accessor functions that we can find in the documentation. And there's a lot of them because you can map different data types to those 128-bit registers. You could map a 2D texture coordinate vector to it, you could map a 3D vector to it, you could map a 4D RGBA color to it. So there's a lot of different accessor functions. If we consider an XYZ vector, a 3D vector, then we may want to use a function like XM vector set X or SM vector set Y. And if we look at the documentation and details of it, it takes an initial XM vector and an X value and returns this XM vector with the X value modified to this new X value. So it's a little odd in how you access it, but if you're going to do a lot of vector operations or a lot of vector transformations in this XM vector type, it's worth going through this odd accessing hassle in order to get advantage of the performance improvements of the XM vector type. So let's see some example. This is a program that we've looked at previously that just draws a triangle, and I've made a couple of changes. In particular, I changed the matrices to be world view and projection to be of XM matrix type. And we also added this using namespace DirectX, so we don't have to prefix everything with a DirectX : : Also, the camera position that we've seen is also one of these XM vector types. In this particular program, as we saw previously, all it does is it has a triangle that rotates around. If we look at the matrices and find out how they're actually used in the program, first of all, in the initialization part of the program, you see that we set them all to the identity matrix, and there's a XM matrix function for that. We can, in the update here to do the rotation, we set the world matrix to an XM matrix that's rotating about the y-axis. We set the view matrix equal to an XM matrix function that gives us a viewing transformation matrix from a camera position, a look point, and an up direction. When we do the rendering, recall that we had to pass in the combination of world view and projection matrix to the shader program. So we use the overloaded multiplication operator for XM matrices to multiply them together. And then also recall that HLSL expects for matrices to be in column order, so we have to take the transpose, so we use the XM matrix transpose function. On the camera position, which is a vector, we're treating that as a three-dimensional vector. Initially we set the camera position to have a z-value of -20, so we're backed away from the origin a little bit, and we use the XM vector set function to do that. When we update the camera position, in the case of the user pressing a key down to back up, in this case what we're doing is a vector operation, so we're saying that the forward direction is positive z. So we're creating a vector for forward direction being positive z, and then we're multiplying that by some value, some negative value, which means essentially saying back up. So we take the initial camera position and add to it some fraction of a positive z. In this case it's a negative percentage of forward, and so negative forward is backwards, and so we're backing up a little bit. Another possibility that would accomplish the same thing is to write camera position equals XM vector set X, and then pass in the camera position, and then pass in the new X value that you wanted to set it to. And that would be a little bit challenging to get, because you have to do, I believe it's XM vector get X, so you could write this line that way as well. So it's a little bit cumbersome. It would be nicer to write camera position dot X, but because this XM vector is mapped to a special floating point register, we don't have X as a data member. Instead we've got these odd values here which map to arrays of basic data types that happen to fill that 128-bit register. So in this case, for a float 32, it's an array of 4 of them. In this case, for an integer 16, it's an array of 8 of them, and so on. So we just have to get used to accessing them with XM vector get and XM vector set functions. Some of the common operations that you're probably familiar with in other work: you can add and subtract vectors. You can scale a vector by, there's a few different multiplications. You can scale a vector by multiplying it by a scalar, so that will increase or decrease the vector's length. You can do dot product on two vectors, which gives you a result that's relative to the angle that the two vectors make. You can do a cross product between two vectors. One really common use of a cross product is to get a perpendicular vector. So if you have two vectors, if you take the cross product of those two, the resulting vector will be perpendicular to those two. It's good for creating normals. And another good example is on the camera. If we take the cross product of the look at vector and the up vector, then that would give us a left direction. So sometimes in first-person shooters they may call it a strafing, where you move side to side. In order to get the left vector, you could take the look at position and do a cross product with the up vector. And that would give us the left direction. And of course the right direction is just left direction times -1. Length and normalize, pretty common vector operations. Projection and reflection, maybe not quite as common. There's an image here, it's worth looking into this. The projection of the vector u onto the vector v. So if the vector v is the blue one, and it doesn't matter how long it is, and it doesn't matter if it's in the negative direction, it could be in, the vector v could be in this direction. The vector u projected onto the vector v is the green vector here. So you can have a vector projected onto another one. That can be a useful thing sometimes. To do a vector reflection ends up using projection in the formula for it, but there's actually a function for xm vector reflect, and that'll give you a reflected vector that's useful in some lighting calculations and also for physics, obviously. Refraction is not as commonly used. Sometimes in special lighting effects you might use refraction. So again, we've got information here on dot product and cross product. There's another vector operation we don't do as much on the CPU, but we do sometimes on the GPU, and they call this component-wise multiply. Sometimes in a textbook you might see it as the Hadamard product. In our book they use this symbol here, a circle with an X in it, and basically it's a component-wise multiply of all the values. So it's the X values multiplied together, and the Y values multiplied together, and the Z values multiplied together, and the B values multiplied together. And we'll see that later on in some shader programming when we do different lighting calculations. We've seen this a little bit before. We're going to look at it in a little more depth, and that is information about transformations. And we can categorize them in different ways. One way that I categorize them is into world and view and projection transformation. And we've seen the view transformation that uses the camera position, the up vector, and the look point. And we've seen the projection transformation that uses the field of view and the aspect ratio and so on. Here we'll look at some of the world transformations in a little bit more detail. We've talked about the scale, rotation, and translation. Let's actually do some of these transformations. And if you go to the documentation, you will see that you can find rotation functions, you can find scaling functions, and this is only a partial view. As we've seen earlier, there's also a translation function that can be useful. So let's take a look at an example one of the things that we could do is draw two instances of this triangle. And one possibility would be to create a scaling matrix and you can have different scale factors in different directions. So if I wanted to make my triangle half as big, and then set that as the world matrix, then when we render this, you see that the triangle is no longer spinning or rotating, but it's just staying in place, and it's drawn smaller because we replaced the world matrix with the scaling matrix that makes this smaller. And you can scale it non-uniformly, so if I make it much smaller in the Y direction, then it'll be squashed or compressed in the vertical direction. So you see the scaling in the X is still the same. The scaling in the Z doesn't matter because it's in the plane. It's perpendicular to the Z direction, so the scaling in the Z doesn't really matter. But the scaling in the Y, you see how it's squashed in the Y direction. So I'm going to make a fairly small triangle here, and it's going to be at the roughly at the origin. So this is the origin, and again we can still move our camera backwards. It goes pretty fast. We don't have a forward capability yet. So there's our one rendering. We can do the same thing, draw another triangle, and if we didn't change the transformation, it'll draw at the same location. But if we change the transformation, and so I'll need to make these variables here. I'll just declare them up here so that I can just assign it here, assign it here, and then I'm drawing one, and here's where I'm drawing the second one, but I want to change the transformation. So if I do this as mworld, and if you recall in the update, mworld is still this matrix that's causing the triangle to rotate, we should get two versions of the triangle. So here's one draw indexed where the world matrix is scaled to be fairly small. Here's another draw indexed where the world matrix is the rotation that we set here in the update function. And so we should get two versions of the triangle. You see the larger one that's rotating, and you also see the smaller one when it's not blocked or covered up at the origin. So in this way we can draw two or more versions of the same geometry, but with different transformations. And so if you imagine having something like a rock that's got an odd shape to it that's stuck into a terrain, you can draw several versions of that rock scaled non-uniformly in different directions and rotated and translated in different places, and it would look like different rocks strewn around in a field or something like that. This is a trick that developers use quite a bit we don't have a lot of different geometry. A lot of times it's the same thing, but it's been modified with transformations to look like there's more geometry in our scene than there really is. We can do this with buildings. We can do this with other environmental things like trees and bushes and so on. Let's look at combining transformations. And maybe before that, we'll take a look at some of these matrices. I'm not sure if you recall from the math class, but the matrices are 4 by 4, and we end up multiplying to do a matrix multiply. We multiply a matrix times a vector with this homogeneous W coordinate added, and it's almost always has a value of 1. And an identity matrix has all 1s on the diagonal, and if you multiply anything by the identity matrix, it doesn't change. A translation matrix looks like an identity matrix, but it has XYZ values here in these last, in the bottom row. And depending on whether the matrix is multiplied by the vector in a pre-multiply or a post-multiply form, you may see in some libraries that XYZ is placed here, transposed. And again, this depends on whether you're multiplying the matrix by the vector or the vector by the matrix. In this case, the vector would be here, so you'd be multiplying the matrix by the vector, so you'd get X, Y, Z, and then a 1 here. And so when we got to this last row, nope, sorry, that's incorrect. In this particular case, we would have the XYZ multiplied by the matrix, so that you would get X times 1 and then 0, 0, and then the 1 in the W position times X. So then you would get X plus the translation amount X. So these are the translation amounts, these XYZ values here. In the case of a scale matrix, you see that the scale factors are on the diagonal, replacing the 1s, so that we get X times SX, which can cause X to grow or shrink depending on the value of the scale factor. So a scale factor of 1 doesn't change anything. A scale factor of 2 makes something twice as big. A scale factor of 0.5 will make something half as big or smaller. Rotation, I don't have an example of rotation here. The rotation values end up being, depending on whether it's X, Y, Z, the rotation values end up being in this part of the matrix, in the first 3 by 3 values. Those are the rotation values would end up being in that part, and it depends on whether it's X, Y, Z or rotating about an axis. It's a little bit more complicated. The other thing that we've seen is that you can combine matrices by multiplying them together. So if you wanted to do a scale and then a translation, you can do that by multiplying the matrices together. And it's really important to remember that the order that the matrices are multiplied is really important, because in linear algebra, matrix multiplication is not commutative. So that means if you have two matrices A and B, A times B is not necessarily the same thing as B times A. The order of the transformation is important. So let's see if we can do that. We'll take our large I'm going to move this rotation code down to the rendered just to make it a little bit easier to work with. So this is the first scaled matrix here that we're drawing at the origin, and then this is the second one that we're going to kind of move around or play around with. So we have a rotation matrix that we've creating, and every time we call render, the angle is going to increase by a little bit. So we'll have a slightly different angle every time. I'm going to create a scale matrix now, another scale matrix. We have one. Let's make a different one. And we'll create a translation matrix. And we better not use T because that's the transpose. So let's call this in fact, let's do this. Let's call this transpose, so that when we get the transpose, we'll do this, and then we'll set that to the constant buffer, which goes to the shader program. So when we get the transpose, same thing there. So now T will be our translation matrix, if we want to have one. So here's how we make a translation matrix, and the three parameters are the offset in X, the offset in Y, and the offset in Z. So let's say I want to move this matrix 5 units down the X axis and 0 units in Y and 0 units in Z. Now I can combine and make a world matrix that is scaling times translation. The order in which the matrices are created doesn't matter, but the order in which they're multiplied matters. So what I'm doing is I'm making another triangle that's going to be not quite as small as the one at the origin, but I am shrinking it by half, and then I'm moving it 5 units in the x-axis. Let's see if that was far enough to... So here is our scene right now. The first one is scaled to be fairly small, and then the second one is scaled to be half as big as what it was, and it's moved 5 units down the x-axis. And notice that we scaled it first and then translated it. So what would happen if we were to reverse that? If we were to translate it first, we would take the large triangle and move it 5 units down the x-axis. So we'd get a really large triangle here. And then we would scale it, and by scaling it, it makes it smaller, but it also moves it. So the x value of this point would be scaled to 2.5, so that large triangle then would be drawn halfway in between here. So scaling and translating is very different than translating and scaling, so the multiplication order is important. One other thing here, if we add the rotation, so if I do the scaling and then the translation and then the rotation, what will we see? So notice that the large triangle has been scaled, translated out 5 units, and is now rotating about the y-axis. But it keeps that, say, orbital radius of 5 units away from the y-axis because it was translated first before we started rotating it. In contrast, if we change the order of the rotation and the translation, what that means is that we're scaling it at the origin and then rotating it at the origin and then translating it out. So it's been scaled here at the origin, rotated, and then translated out here. So it's it's rotating about a new origin that's placed here at 5 units. The rotation point has been translated 5 units out on the x-axis. So again, this underlines the importance of the order of the transformations. Another common problem that we can run into, and that is this rotation about a pivot. So for example, if we wanted to rotate an object that's not at the origin about the object's center, how would we do that? So in the example that we have over here, we've got a box that's out somewhere in x and y. Let's say this is the x direction. We'll say this is the y direction. So we've got some box or some object that's out in the x and y somewhere. If we wanted to rotate it in place, or let's say if we tried to just rotate it about the z-axis, it would if we wanted to rotate this object about the z-axis, it would rotate either this way or this way, depending on whether we did a positive or negative rotation. And we can figure out which way by using the remembering that we have a left-handed coordinate system. But instead of doing that, if we wanted to rotate it about its center point, we want to rotate this thing about its center point, maybe like this. How do we do that? It ends up being a three-step process. What we do is we translate the object to the origin. So we create a translation matrix. I call this Tn because we're translating into the origin. And the translation amount of Tn is negative of the pivot point. So it would be negative pivot.x, negative pivot.y, negative pivot.z. And that translation then would put the object at the origin. Once it's at the origin, then we do whatever rotation we want to do. In this case, we're rotating about the z-axis. After we've done that translation, then we do after we've done that rotation, then we do a translation back out by positive pivot. So translation by pivot.x, pivot.y, pivot.z, and that moves it back out to the pivot point after it's been rotated. So here we see we have a rotation that's completed about its pivot point. And what you do is you take these transformation matrices, so you take Tn and you multiply that by whatever the rotation matrix is, and then you multiply that by whatever the T out is. And this gives you, this combination of these transformations in the proper order gives you a rotation about a particular pivot point. And so we see things like this. If you want to rotate the propeller of an airplane, it needs to rotate about a particular axis or particular point in space. If you want to rotate the blades of a helicopter, a windmill, Ferris wheel, a lot of things like this, you often want to rotate about a particular point in space. And it involves this process of moving the object to the origin, doing the rotation, and then moving it back out. That's a common trick that we use. Normals. Normals are often used in lighting calculations to represent the perpendicular direction to a surface. So you've probably seen outside in a sunny day, if you get in a bad place with say a car windshield, you get a really bright glare. If you move away from the perpendicular direction of that windshield, you don't get as bright a glare. And so normals are often used in lighting calculations, and they are just direction vectors that are perpendicular to a particular surface. For a sphere, all the normals are always outward facing. So if you have a point on the sphere, you can get the normal by direction by subtracting that point, subtracting the origin from that point, and then normalizing it. And a normal is just a direction vector. It doesn't have a starting point or an ending point. It just represents an orientation. So you take the point on the surface of the sphere, subtract the origin from it, and that gives you this displacement vector. And then if you normalize that vector, that gives you the proper direction. And again, it doesn't matter where it's placed. It just matters what the direction is. And so for a sphere, all the normals are obtained by taking the point on the sphere, subtracting the center, and normalizing. For a plane, if we wanted to get a normal to a plane, or in our case a triangle like a polygon, we can take two edges of the polygon and do a cross product. So in this particular case, in this example here, if we know the three vertices of our triangle, P1, P2, P3, we can compute V1 as P2 minus P1. We can compute V2 as P3 minus P1. And then we can compute the normal vector as V1 cross V2, or V2 cross V1. And the difference is we'd get a normal vector in one direction, or a normal vector in the other direction. And so sometimes when we compute normals, we may accidentally get, say for a box or a sphere or a curved surface, we may get inward facing normals when normally we want outward facing normals. So it's not an uncommon operation to try to reverse normals. When we get to doing lighting calculations in our shader program, we have to somehow transform the normals by our world transformation matrix. And it's a little more complex than that because a normal is just a direction, it doesn't have a location. We don't want to scale the normal, and we don't want to translate the normal. So in order to properly transform a normal by the world matrix, what we end up doing is zeroing out the translation components and using just the upper 9 by 9 or 3 by 3 rotation components to do the transformation. And it's a little bit more complex than that because we don't want to include the scaling. So to get rid of that, we end up doing the inverse transpose. And there's a math proof in our book if you want to look that up, and there's also a function in our mathhelper.h that we've looked at. So the basic steps for getting the proper matrix to transform a normal by our world transformation is to take the world transformation and zero out the translation components, and then take the inverse transpose of that matrix. Fortunately, we already have a function for that in our math helper. There is a function called inverse transpose. And what happens is we take the last row and set it to 0, 0, 0, 1. So we're zeroing out the translation x, y, and z components. And then we're inverting the matrix and then taking the transpose of that. And that gives us the so-called inverse transpose with the translation taken out that we can use to transform our normals by the orientation components of the world transformation matrix. And we'll need to do this for lighting calculations. So if we have an object that's rotating, we want those normals to change orientation based on the rotation that's applied to the object. And we'll see that more when we do the lighting calculations in the future. So that concludes this presentation on DirectX Math programming. We've seen the vector operations, and in particular the vector types that are mapped to special registers on the CPU for performance. We've seen how to do different vector operations with functions for things like add and subtract, cross product, and so on. We've also seen some matrix operations, how to create typical transformation matrix like scaling, rotation, and translation, and then how to combine them with multiplication, paying close attention to the order of those multiplications, because the order matters in a lot of cases and can get us the right effect that we're looking for. So let me know if you have any questions. I hope this helps you out with understanding more about DirectX 11 Math.